So you were talking a lot about the electrostatic force, right? And well, what is the relationship, right, between that and the gravitational
Hmm.
force? Interestingly enough, it's literally
Mm.
the same thing.
Yeah,
It's
very
literally
similar.
the same thing.
Very
Like
similar.
like the equations, like for those physics guys out there that know the Coulomb's law, probably know from grade 12 first year physics. So Coulomb's law is literally Newton's gravitational law, just changing, the mass for the charge and the universal gravitational constant for the Coulomb constant. So it's
Hmm.
literally the same thing. But again, as I mentioned in the beginning, we're not really going to be talking about the equations itself, but the relationship. So, what is the relationship? And again, the fact that gravity, we know gravity has an inverse squared relationship, right? It follows the inverse square law. So, you go 2 meters away, gravity drops by a fourth. You go 4 meters away, it drops by a 16th, right? So, the idea is that that relationship is held in electrostatics as
Hmm.
well,
Yeah.
right? So it's inversely proportional to the distance squared between them. So the
Hmm.
farther, so if you have two protons, or I guess let's not get into magnets, but like if let's say we have two protons, not that you really are playing with two protons ever, but that's why the magnet example would be better to explain. But in two protons, for example, the closer they are, the stronger they will feel that repelling force, right?
Hmm.
But what's interesting about this force isn't the fact that there is a force itself. At least to me, what's really interesting about this electrostatic force is how, seemingly, like even with gravity, when we have things like, 5 light years, okay, maybe light years a little too much, but like 2 astronomical units away, like the sun and let's say Pluto or like some planets, like 2 astronomical units away, there's still a force that is attracting them. Now, we've spoken in higher classes about general relativity and stuff like that, but let's just not go there right now. What's interesting about the electric definition is that there's somehow, even with like, if let's say they're 2 astronomical units away, there's still some kind of connection between them. But on gravity, it's understandable because it's space. You're on space, so what's connecting the two? Space. But what's connecting the two charges in the electrostatic force, right? And that would be the electric field, right? So the interesting thing about the electric field is that it permeates through all of space. And the electron is just small excitations in this field. And the proton is similar, again, to do with electric charge, right? So the fact that they can communicate with each other even when they're like 2 astronomical units away. Again, I'm just giving a large distance. There's no significance to this number whatsoever. But when it's a large distance away, they can still communicate because of the fact that every charge emits a field. And that field, theoretically speaking, resonates through all of space, right?
Hmm.
And that's that
The, the
cool
the one
thing.
thing
Yeah.
the one thing with that is, yeah, technically,
Mm.
if there's a charge that's on Pluto right now, it does affect the electrons in your
It
body.
does. It
But
does.
if you actually work out the numbers on it, because you have to plug in like the charge of like over there multiplied by the charge over here to calculate the force, as I mentioned earlier, that in SI units, which is, newtons are in SI, and so if you want to calculate like the force in newtons, you use that like really small number for
Mm.
charge. And so in comparison, if you have like I don't know, 1 kilogram attracting another kilogram, the gravitational force, it actually I'm not even sure this is true, but it just it in my head it appears as though the gravitational force is stronger than
It's literally
like,
not. It's the
but it's
same thing, though.
not.
It's
It's not.
literally the same thing.
No, it's not the same, right? I mean,
Well, because of the units, yes, yes, because of
yeah,
the
yeah.
units, it's a lot. Well, that's only if you're comparing electrons, though. You're
I
comparing like
know,
something
but what
one
I wanted to get
kilogram.
into, I know, but what I wanted to get
Okay.
into was to be like, oh, it appears as though the electromagnetic force is weak and the gravitational force, holds like planets together and all that stuff.
Mm.
But I don't know if I've said this before on the podcast, but if you take the weakest magnet you can find in your house and you attach a paper clip to it and you you hold it above the earth, just know that the electromagnetic force holding up that paperclip from that tiny, tiny magnet is stronger than the entire gravitational force of the Earth, which I think I have said before on the podcast.
Yeah,
but
I
that's just
recall you saying something like this.
that's
But
that's just a fun fact.
yeah, I mean that's what you
everyone
can
should know.
understand, right? Because the distance, it's all about that distance.
Yeah.
Because when you're holding it on top of the Earth, you're 6,000 kilometers from the center of the Earth. But when the magnetic clip is literally attached, or sorry, when the metal clip is literally attached to the magnet, the distance is 0, right? Because they're attached together. So like you're I mean that's that comparison, right? So there's definitely a difference in force, and the interesting thing is that they're kind of based together, and that I don't know if it's a meme or if it's a joke or whatever, but it's that very common thing that, like Newton writing a paper and then Coulomb looking over and copying the equation because it's the exact same equation.
Yeah, it looks the same.
Yeah, because it is. But again, that's just a nice thing to see in how we can compare electrostatics to gravity, right? Something macro to micro.